This video covers classification and regression trees, and these are techniques that you can use both for gradient analysis, so if you want to establish associations between predictor and response variables, or you can also use them for predictions, so similar to a regression problem. Now, classification and regression trees is abbreviated in CART, and it depends on your predictor variables what you're actually carrying out. So it's classification trees if your predictor is a categorical variable, and it's a regression tree analysis if your predictor is a continuous variable. And then we also have the multivariate version of classification and regression trees. That's abbreviated MRT. I don't know why they leave out the classification, but it is a method that does both classification and regressions. So let's see where we sit in our objective matrix. So classification and regression trees are all virtually assumption-free. They're also non-metric. Multivariate regression trees is a constrained gradient analysis. So I'm looking for relationships between a set of predictor and a set of response variables, and I'm just looking at what they have in common. And the univariate regression trees, you can think of them as an alternative to a linear model. So an alternative to either a simple regression with one predictor and one response variable, or a multiple regression problem that has many predictor variables and one response variable. And it doesn't really matter how your data is distributed or how your relationship looks like. So CART really is an alternative to all kinds of other techniques. You can also predict classes, replacing discriminant analysis, or your response variable can be a 1 or 0, so presence, absence. It would be an alternative to a generalized linear model. So it's very powerful for predictions, and in the lab we'll actually also go through a version of classification and regression trees that's specifically designed for predictions. So it's a bootstrapped classification and regression tree that's working with subsets of your data rows and subsets of your variables, and tries out a large number of combinations to make those predictions. That's called random forest. It's actually a machine learning technique. It's not deep learning, it's a shallow machine learning technique. We'll run an example in the lab, but in principle it works exactly like CART. Okay, if you recall our last video on gradient analysis, we ended up with a little bit of a disappointment in that those gradient analysis can't detect any unimodal relationships. And for you to recall what that means, for example, if I have a species frequency of a species 1, I plot that over a gradient, I may have a situation where it's too cold at this end, so the species doesn't occur there or doesn't grow very well. Then I have some sort of maximum where the species does best, and then it declines again where it's getting too hot. So these are actually very typical response functions for species. They almost always have some environmental optimum and then other conditions where they have a competitive disadvantage. Now if I have a relationship like this and I were to fit a model that assumes linearity, so a straight line right through, so I get a correlation of 0, even though mean annual temperature surely is an important predictor variable for the frequency of the species. So an ordination just can't do this justice. If we imagine that this is one species out of a bigger ordination, the species vector would point toward the circles here, so those are plots where the frequency is high, and then at the other end of the plot we would have the triangles and the squares where the species frequency is low. So my species vector I can easily point in the right direction. But now if I do a direct or indirect gradient analysis or a constraint gradient analysis, in all cases I can't place that environmental vector. So at the same time I would have to point the vector towards high and towards low value in this corner here, and that just doesn't work out. So regression trees offer a solution here. So what I can do instead is I can divide my data set recursively. It works essentially like a top-down cluster analysis, like a divisive cluster analysis, which we covered before. Except in the normal cluster analysis, what I'm going to try is to find groups that are similar based on one set of variables. So, for example, my species frequency. So in this case, I would probably group my squares and my triangles together and my circles. So it doesn't quite give me what I want. But I can use a second set of variables as my predictors, and that's what regression tree analysis does. So I'm grouping one set of variables, but I use another variable set as partitioning criteria. So I can't say I'm going to group the triangles together because they have the same low frequency. I have to use another variable set to make those decisions. So I can say I want to group my squares together because they have all low frequency. So I'm going to go left if mean annual temperature is smaller than 2, and then the other two are on the right side. So I can subset these again. So this time I'm working with a subset of the circles and the triangles, and those I can distinguish by a mean annual temperature value of 4. So I'm finding groups with minimum variance within my groups, but I'm using another variable data set to do that. So I'm not using just the species frequency data to come up with my groups. So that way I have beautifully described my frequencies in this hump-shaped distribution here. So if temperatures are larger than 4, it's going to be low frequency. If they're smaller than 2, it's going to be low frequency, but for the intermediate values between 2 and 4, there I have my high frequencies. So any kind of relationship between a predictor and response variables can be modeled that way. So obviously I'm not restricted to just 3 classes, so I just did this here for simplicity. This can be quite an elaborate tree, and it can also use multiple variables as decision criteria. So this is just to illustrate the general principle. Now another very interesting feature of multivariate regression trees is that they can model interactions very well. And so I'm creating another simplified example here. Imagine that we have a mountain range that goes from north to south. And so in the north, the mean annual temperature is 2 degrees, and in the south, it's 12 degrees. So it's quite a latitudinal range that we are looking at here. And when it's cold, I have a species that likes to be on the south side of mountains because it's relatively warm here. And in the south, it's actually getting too warm on the south side, so that's where the species is on the northern slope of those mountains. So if I have slope and temperature information with normal linear models, it's actually quite difficult to figure out where the species occurs, right? Because it occurs at high temperature and at low temperatures, so there's apparently no information there. And it also occurs at the northern and at the southern slope of the mountain, so I can't use it as a predictor either. So it's all flat relationships if I look at them individually. But in regression tree analysis, I can break it up, right? So I can say, okay, first of all, I'm breaking my presence-absence data set up by temperature. So I'm looking separately at anything that's larger and anything that's smaller than 7 degrees. And then after that split is done, I'm looking at north and south separately. So if I have a combination of warm temperature and northern slopes, so warm temperatures here and northern slopes, that's where I have high species frequencies. And if I have a combination of cold temperature and southern slopes, that again is where I have my high frequencies, and for the other combinations, frequencies are low. So it's an extremely flexible technique that can handle real-world interactions really well, because these things really do exist. So there's, for example, also very often interactions between temperature and precipitation. So for example, if precipitation is high, species tend to be able to tolerate higher temperature than if precipitation is low. And another advantage is that you can use class variables as predictors. So we've done it already here. They don't have to be numeric. I can use classes as criteria. So in this case, you would go right if my slope is north, and you would go left if my slope is any other value, like southeast and west, and the same would apply for this break here. So we have another example later on, but you can also imagine that your class variable is a response variable, right? So I can go through this here and say, okay, if my mean annual temperature is larger than 7, and I don't know, my precipitation is larger than 15, maybe then I have a coastal western hemlock ecosystem here, so a class could be at the end of those leaves. So these techniques can be used as data mining tools in a very flexible way. So if you want to figure out what kind of risk factor are associated with heart attack and other disease classes, you could use these types of regression trees. And so it can be used for both the association. So in this case, we just want to understand how species are associated with environmental variables. So in this case, we figured out what kind of combinations of temperature and aspect are beneficial for species growth or species frequencies. But you could also make predictions. So let's say I have a new site and I want to predict the frequency of a particular species. So if I had a new site with a temperature of 10 degrees Celsius and a southern aspect ratio, I start my tree and I go and say, okay, MAT is larger than 7 or smaller than 7? It's 10 degrees larger, so I'm going right. And what is my aspect ratio? South, so it's not north, I have to go left, and I would arrive at this value, and I predict that the species frequency is relatively low. So that's how predictions are done with regression trees. So let's take a look how the algorithms actually work to run a cart analysis. It's a trial and error method. So what you do is, if you have some sort of relationship between a species and a predictor variable, let's say it is a simple linear relationship, what you do is, in the first step, you split your data set into two groups, group 1 and group 2. And you can move this threshold here, this MAT threshold, around either to the left or to the right. And your goal in doing this is to create two groups that minimize the variance within groups. So what you want is as homogeneous a group as possible based on the position of your threshold. So it's a recursive trial and error algorithm that moves the slider here to the left and to the right, and then looks at the variance in your groups, and then it picks a threshold that gives me the least variance within groups. So that's a regression tree version. If I have a classification tree version, so I have a class as a response variable, so this could be absence and presence, and I'm putting my plots here just as I did here, where my species occurs or where the species doesn't occur. So again, I can move my slider to find two groups, group 1 and group 2, that are as homogeneous as possible. Now, you can't get a perfect solution every time, so in this case I do have some errors, but it's the best I can do to maximize the homogeneity within my groups. But let's say I move my slider further to the left to get rid of this point here, then I actually introduce two more errors here to my group 2. So again, it's a trial and error to minimize these errors here, those red points, and maximize my homogeneity. So I'm trying different thresholds. I'm also trying different variables. Maybe I can do a better job minimizing the variance or getting clean groups with another variable. So if it was mean annual precipitation here, that does a better job to get two really homogeneous groups, then that would become my criteria to distinguish my two groups. So I try many different thresholds for all the different variables, and then I pick in the end the best one I could find. So it's a trial and error mechanism. And that's my first split of the regression tree. And then I do the same thing again for both subgroups. So I'm repeating this whole procedure for my group 1 and split this further up. And then also I do it for group 2 and split that further up. And as we've noted before, you can use class variables as predictor variables. So I just wanted to show you how that would work in principle just the same way. So instead of a slider that I can move left and right, I actually have to try out all possible combinations of that predictor variable. So let's assume we have soil type and we have present and absent data at plots. So for my soil type A, I have 2 plots where the species is absent and 6 plots where the species is present. And then for my soil type B, I have 8 plots where the species is present and 1 plot where the species is absent, and so on and so forth. So I arranged these things slightly differently here for a class variable. And now I can try all combinations to get clean groups. So I could ask, well, what if I look at my soil type A versus all the others? Does that give me good groups? So in my group 1, I have 6 presents and 2 absents, and in all my other groups I have 6 presents and a lot of other absents. So it's not an optimal solution, but I highlighted here things that are similar. If I arrive at the permutation where I look at group B and C versus A and D, and that actually gives pretty clean groups, right? So I have, if I combine B and C, that species is mostly absent here. I have only 1 presence. So that gives me a combined group with low frequency. And A and D are sort of intermediate, so 0.61. And now I can basically do this recursively. I can break those 2 up, but they're already quite similar, so I may not choose this as a next step. But I can break A and D up, right? So I can look at A versus D in this branch of the tree. And in that case, I get relatively high frequency, so 6 out of 8 is a 0.75 frequency versus an intermediate frequency for D here, that's a 50-50. So that way I can come up with a regression tree that models species growth or species frequency as a function of soil type. And also that I can use for predictions. So if I know I have a soil type D for a particular plot, I can follow my regression tree. I start here, okay, D is on the left side, I have to go left. Then at the next node D is on the right side, I have to go right. And my prediction for that soil type, I have a 0.5 frequency of that species. And an additional advantage of this approach is I can also do that for multiple response variables at the same time. So that's actually extremely easy to imagine how that works. So I just simply look at two species over MAT plots at the same time, and my slider here goes left and right simultaneously for both species. And again, I try to maximize homogeneity or minimize within group variance by moving that slider left and right, except now I look at two response variables at the same time. So in that case, if I put my slider here at 3 degrees Celsius mean annual temperature, I'll get fairly clean groups. So my group 2 is perfectly clean and my group 1 has 1 error here and 2 errors there. So larger or smaller 3 degrees Celsius could be my first split in a regression tree. And again, the same principle applies. I would look at other variables as well, besides mean annual temperature, and it works for both continuous and class variables as predictors. So if I report the results of the regression tree, at the nodes here at the end, you not only get results for one species, but for multiple species. So let's say we have 5 species. You can get these little bar plots, or they're also sometimes called leaf plots, of 5 species that show their growth or their frequency or whatever your response variable is. So if I look at all my plots, maybe that's n equals 20, I may on average across all my plots, my species 3 is most frequent, followed by 4 and 1 and 2 and 5. So now I have different conditions and I can see how my species respond to this. So maybe my first break that minimizes the variance within my groups is if I break at larger 10 degrees Celsius. So I have 3 species here, 2, 4, and 5, that don't like it warm. You know, they are much better off in the cool climates here, so they have higher frequencies here than there. That's my first split. So maybe n equals 8 are warm, and n equals 12 are cool. And then maybe I also split this one up again by a different criteria. For example, mean annual precipitation less than 370 millimeters. So these species here like it cool and dry. So particularly the species 1 and 2 benefit from this. So species 1 and 2 like it cool and dry, and 4 and 5 like it cool and wet. And species 3 here is actually relatively unaffected by all my temperature or precipitation criteria, so they have similar frequencies in all cases. Now, these little leaf plots are sometimes a little hard to interpret if you start with different frequencies. So one thing I like to do and that I recommend before any kind of regression tree analysis is to standardize your response variable. So if you do that, you get exactly the same results, but it's much easier to interpret. So your first leaf plot is actually flat. There's nothing because they all have a mean of 0. So one standardization is to take your columns, subtract the mean, and divide by the standard deviation. So that weighs all species equally and sets the mean to 0. And then in the first split, you can right away see, okay, species 2, 4, and 5 have below average frequencies if temperatures are high and above average frequencies if temperatures are low. And then if I add the second split here, the mean annual precipitation, I can read off the results much easier. So species 1 and 2, they like the cool and dry conditions, not so much the cool and wet conditions. Species 3 has average species frequencies everywhere, and then the 4 and 5 here, they don't care about precipitation, but they do care about the temperature difference. So it's a little easier to see it if you express it as a standard deviation from the mean. And so in R, you can use the scale function to set the mean to 0, so that the center equals true. And if you want your variable units not to matter, then you can also set the scale to true. So that means divide by the standard deviation. So what that does, it weighs each species equally. So that's one option. And there are actually a bunch of other transformation options here in the vegan library. So there's a decostand function that does a standardize. That's just the same as the scale with those options, or with the default scale command. But there are also other widely used transformations, like Hellinger transformation, Wisconsin transformation. So they do similar things, but they, for example, Hellinger uses square root transformation just to rein in the very frequent species and exaggerate the rare species a little bit in your response. So there are a bunch of options to transform your response variables, to make it easy to interpret and to weigh your individual response variables the way you like it. Now, one thing that you never need to do, though, is to transform your predictor variables. So this truly doesn't matter in these regression trees, because it just looks for a threshold, like 10 degrees Celsius in this particular case. So if you transform this to any other value, let's say a log transformation of mean annual temperature, it will just find that value in the transformed data. It will just set the threshold to a different value, but it doesn't change anything in your regression tree. So if you want, you can try this out. So however you transform your predictor variable, it never has any kind of effect on your regression tree. So it's a completely non-parametric technique. So you can use it with any kind of data, even class variables. So very useful technique, extremely flexible, and very powerful in making predictions based on big multidimensional data sets. So with that, we'll move on to the lab number 8, and you can try all of these things out.